Good morning everyone. I am Chandrika from the Department of Electronics and Communication Engineering at Srinivasa Ramanujan Institute of Technology. Today I am going to present my continuous alternative assessment on the subject of signal systems and stochastic process. Today the topic of my presentation is power spectral density, definition and the expression. Contents of the power spectral density, definition and expression. Introduction, definition, purpose, expression, terms used, alternative definition, Weiner-Khinchin theorem, units of PSD, types of spectral density, PSD estimation methods, graphical representation, significance, applications, conclusion. Introduction. Power spectral density describes how the power of a signal is distributed across different frequencies. It helps to analyze signals in the frequency domain, showing which frequencies contain more or less power. Mathematical expression is S summation xx of f t tends to infinity limit t1 e of modulus xt of f into 2, where S of xx of f is the power spectral density, xt of f Fourier transformer of signal, x of t is the expectations or average value. PSD is also related to the autocorrelation function by the Weiner-Khinchin theorem. Sxx of f is equals to integration of minus infinity or summation xx into tau e minus j 2 pi of f by d pi. Definition. The power spectral density of a signal describes how the power of a signal is distributed over different frequency components. In other words, it shows the which frequencies contain the signal's power and the how much power is present at the each frequency. It is a fundamental concept in signal processing and the communications, used to analyze random or time varying signals in the frequency domain. For a continuous time signal x of t, the PSD provides a frequency based view of its average power content. Purpose. The power spectral density is an important concept in signal processing that describes how the power of a signal is distributed over different frequencies. The main purpose of PSD is to provide insight into frequency content of signals, especially when dealing with random or noise-like signals that can't be easily analyzed in the time domain. In practical terms, PSD helps determine which frequency components carry the most energy or power. This information is essential for understanding the nature of a signal, how it behaves under different system conditions. For example, in communication systems, PSD analysis helps identify the bandwidth of the signal, the presence of noise, and how power is spread across the frequency spectrum. For continuous time signal expressions, alternative form. For discrete time signal, terms used in power spectral density. X of t, input or continuous time signal under analysis. X of f, Fourier transformer of the signal x of t, presents its frequency components, or summation xx of tau, autocorrelation function of x of t, measures the similarity of the signal with a time shifted version of itself. Tau, time delay or lag variable in the autocorrelation function. S of f, power spectral density, shows how the signal's average power is distributed over frequency. F is the frequency variable in hertz, representing the spectral axis. T is the observer time duration used for averaging the signal's power. Angular frequency is the omega. K is the lag variable in discrete time autocorrelation. Alternative definition of a PSD PSD of a signal represents average power unit frequency contained in the signal as a function of frequency. It also can be defined as that expression. X of f is the Fourier transform of the time limited signal x of t. T is the observation time and the S of f gives the distribution of signal power over frequency. This definition expresses PSD as a normalized coordinate magnitude of the signal's Fourier transform. Weiner theorem establishes a fundamental relation between the signal's autocorrelation function and its power PSD. It states that the power spectral density of a wide sense stationary random process is the Fourier transform of its autocorrelation function. Mathematically, expression is conversely. Units of PSD. Definition reminder. Power spectral density PSD represent the power of a signal per unit frequency. Units for electrical signals. If the signal represents voltage, units of S of x equals to V square by Hz. If the signal represents current, units of S of x A square by Hz. For general power signals, units of S of x equals to watt by Hz. Types of spectral density. Power spectral density represents the power per unit frequency of a power stationary signal. Shows how the average power of a signal is distributed over frequency. Used for random or continuous time stationary signals. Examples: noise analysis. Units: watts by Hz, V square by Hz or A square by Hz. Expression. Energy spectral density represents energy per unit frequency of energy signal. Shows how the total signal energy is distributed across the frequencies. Used for signals with finite energy. Units: joules by Hz. Joules per Hz or V squares per Hz. Expression are there. PSD estimation methods. Power spectral density estimation methods of a signal can be estimated using various time domain or frequency domain methods. These are the classified into non-parametric and parametric techniques. Non-parametric methods: periodogram method, Bartlett's method, Welch's method. Parametric methods: auto-regressive AR method, moving average or ARNA methods. Graphical representations of a power spectral density is the PSD shows how a signal power is distributed over frequency. X-axis frequency Hz, Y-axis power per unit frequency. Peaks, dominant frequency components, flat region, white noise, broad peaks, band limited or random signals. Area under PSD curve, total average power of the signal. Provides a visual understanding of signal power variation with frequency. Significance of a power spectral density. There are many significances. Explained someone. So shows how signal power is distributed across different frequencies. Helps in identifying dominated frequency components in a signal. Useful for analyzing random and noise signals in communication systems. Applications are also many. Applications of power spectral density: communication system, signal processing, vibration and acoustic analysis, biomedical engineering, radar and sonar systems, seismology and environmental monitoring. Conclusion. The power spectral density is a vital concept in signal processing that shows how the power of a signal is distributed across the different frequencies. It provides a frequency domain representation of signals, offering better insight in their characteristics than time domain analysis. PSD helps in identifying dominant frequency components, noise level and the bandwidth of signals. It is widely used in communications, analysis, biomedical engineering, and aesthetics. By using PSD, engineering can design filters, improve signal quality, and analyze system performance effectively. In summary, PSD serves a powerful tool for understanding and analyzing signals in both theoretical and practical applications. Thank you, sir.